Welcome back, everybody. So we're going to have Max Hopkins, and he will tell us more about high-dimensional expanders.
Thanks. Okay, so the basic structure of this talk, I'm going to talk. Last talk we saw sort of how to develop the spectral theory. By the way, is the sound okay? Did I put things? Sounds good. Okay. We developed sort of this L2 or spectral theory that we saw. I didn't explicitly write out approximate Parseval, but we saw this approximate orthogonal basis. You can imagine it's easy to recover this type of L2 type result. In this lecture, we're going to look at relations to higher moments, things like hypercontractivity that we discussed. And I won't actually prove hypercontractivity on HDX for you, but hopefully I'll sort of convince you that you should at least be able to do this morally. There's actually one thing I wanted to mention before I go off into this higher norm vein, which is we saw in the last talk this approximate eigendecomposition. I just wanted to mention that you can actually use this approximate eigendecomposition to get bounds on the real spectrum of these operators, so the down-up walk and the noise operator. I mean, this is maybe sort of obvious if you're familiar enough with linear algebra, but I just want to mention that you can prove fairly directly that like the spectrum of, say, the up-down operator or of any of these walks is actually concentrated in strips around these approximate eigenvalues. So the spectrum of this sort of looks like k minus I over k plus or minus O of gamma. And similarly, you can prove that the spectrum of the analog of the noise operator that we talked about will also look like rho to the I plus or minus O of gamma. I mean, this is not something explicitly you really need because you already have the approximate decomposition, but it's nice to know that you can get these sort of stripped bounds on the spectrum of the operators. Okay, so I just wanted to mention that. And now let's actually talk about this sort of higher norm beyond spectral type behavior on HDX. So let's recall from, I think it was in Noam's talk that, or maybe even in Esti's talk, this was mentioned. So I'm going to recall a simple version of hypercontractivity that's typically just called the Bonami lemma. I'm not sure it was actually introduced in this form, but this is like niceness of low degree functions. The Bonami lemma states roughly, or some simplified version of the Bonami lemma says that if I have any function on the hypercube, and I look at its like degree I part, that the low degree parts of the Fourier decomposition are smooth or nice in some sense, in particular, that I can compare the 4 norm of Fi, and it's not too much bigger, some factor of 2 to the O of I here. People know the exact answer, but we're going to be happy with some approximate thing here. Versus the 2 norm squared, or I can just think of this as 4 norm versus 2 norm. And we also saw that this had some really nice applications within Boolean Fourier analysis. The one that I want to recall is small set expansion. And I'll probably sort of take this as my thing that I'll focus on throughout so that I don't have to talk about Bonami. So we saw that this had an application to small set expansion of the noise operator of T rho. Maybe we'll just think of rho as a constant. I'm not going to deal with what the exact dependence on rho is in these things either. We basically saw that if I drew x from the cube, and then I draw y as like a noisy copy of x, right? Resampling each coordinate with, say, half probability or probability 1 minus rho. With this, we take like a rho noisy neighbor of x. Then Noam proved that the probability that for any set, for any subset of elements in the strings in the cube, for any subset of the cube, that the probability that y lies outside of A, given that x was in A, so you can also think of this as, conditioned on being in this set A. When I apply this random walk, what's the probability that I leave A? This is typically called the edge expansion or edge isoperimetry of this type of set. And he proved that on the cube, this beautiful statement called small set expansion, that this is at least 1 minus the density of A to some constant that I'm not going to worry exactly what the constant is, but what this says is that small sets expand near perfectly, right? I think it was stated that sort of much of the mass is near the boundary is one way to state it in terms of these balls. But we got this type of small set expansion behavior. And one way to think of this in the world of sort of versus spectral expansion, which is what we were looking at these eigenvectors and the second eigenvalue, is that in like standard theory, something like Cheeger inequality, the second eigenvalue corresponds to sort of the worst case expansion bounds over T rho. So you could use this type of material to show on an HDX that you have some sort of worst case type of expansion over T rho. But this is a statement that says something different, and it's much, much stronger. It's not that the worst case, like always you have a quarter of edges leaving or something like this. This says if you have a small set, truly almost all of the weight is leaving that set. It's a much, much stronger property. And later we'll see sort of uses of this or variants of this in PCPs and hardness of approximation. I'm going to let Dor do that part of things. Okay, but so the main question for this talk is whether this behavior generalizes to high-dimensional expanders. So, can we generalize Bonami or SSE to high-dimensional expanders? Okay, so that will be our main focus, except that we're maybe jumping a little bit ahead. We haven't talked about hypercontractivity or small set expansion type behavior on any sort of object beyond the cube. I mean, Noam mentioned how you can look at like different types of Cayley graphs, but we didn't really look at domains beyond the cube. And HDFs are not exactly the first domain that you would look at for this type of behavior. And indeed, Noam mentioned one particular domain that's very interesting, which was the p-biased cube at the end of his talk. And so I want to focus first on hypercontractivity on product domains, and we'll give an example for the p-biased cube. And then most of the rest of the talk will be trying to understand why high-dimensional expanders sort of mimic the structure that you'll see in product spaces in the cube, and then why you would expect that we can sort of port certain results like small set expansion and hypercontractivity from products to high-dimensional expanders. That's sort of the overlying structure that we'll go for here. So let's look at product spaces. And I'm sure all of you know what product spaces are, but I'll just be very explicit. So we'll look at spaces where we have some ground set and some distribution over the ground set. So in the p-biased cube, this would be just a ±1, or let's do 0, 1. This would be 0, 1, a bit, and pi might be p-biased, right? So pi might be pi of 1 is equal to p, pi of 0 is equal to 1 minus p. So this would be a single p-biased bit. And then we're just going to tensor this k times. So now our domain is this Cartesian product of k copies. Maybe I'll just write it as omega to the k. And then this comes with this tensored distribution. Write this. Okay, where pi of like, v1 through vk is just the product of each of the individual. So it's just the independent product of these individual coordinates. So let's now look at this simplified question. Can we extend this behavior to product spaces? And Noam already sort of gave a hint to the answer to this in his talk when he was looking at these intersection structures in EKR. The answer is no, at least naively, you cannot do this. And let's see why. So let's look at the example of the p-biased cube. In particular, we'll look at sort of the classical extremal example. We'll look at dictators, which have come up now, I think, in most of the talks. So a dictator 1i, just to be very explicit, we can just think about this as the set of elements in 0, 1 to the k, such that xi is equal to 1, or equivalently, this is just the function xi. And I'm not going to go. Actually, I guess Noam talked about the p-biased characters. This is a degree 1 function, right? It's controlled by one coordinate. If you write it out in the Fourier decomposition, it's one character normalized. And so if we look at Bonami, then we expect, because this is a degree 1 function, if we had hypercontractive type behavior, we would expect that the 4 norm should be like constantly related to the 2 norm. But let's see what actually happens. But if I look at expectation of 1i to the 4th, this is a Boolean function. So this is just expectation of 1i, which is p on the p bias cube, right? Because every bit is 1 with probability p instead of probability 1/2, right? Before we were essentially okay because dictators on the standard cube are not sparse functions. But this is a sparse function and it comes through in this analysis. So now let's look at the squared 2 norm. Okay, same argument, right? This is expectation of 1i, squared, which is p squared. And now think about p as being like asymptotically small with k, like, I don't know, something really small, like 1 over root k or something like this. Then in this case, p is much, much larger than p squared, right? It's like asymptotically larger than p squared. Whereas, again, we expected this relation to be within a constant. So in this sense, the Bonami lemma pretty drastically fails for this type of function. We don't get hypercontractive behavior. And maybe a more direct, okay, we can do these calculations and see that it fails. To me, is coming from like the expansion type of community. It's always more natural to look at the small set expansion version of things. So we can also see that small set expansion is going to fail by the same example. If I look at the probability over x, and then even the p-biased noise, Noam introduced this p-biased version of the noise operator. We draw y, from like the half noisy version. Again, we look at this expansion. We look at the probability that y leaves A, given that x is in, let's set A to be the indicator, given that x is in this set. Well, what's the probability? Remember that we wanted this to be like 1 minus the density of the set. We wanted this to be, in this case, the density is p. It's really small. We want almost all edges to be leaving. But this clearly is false, right? The only way that I can leave the dictator here is if I resample coordinate I. But in the definition of the noise operator, like the half noisy noise operator, I only resample I with probability 1/2, right? So this is at most 1/2 when we expected it to be like 1 minus p to the O of 1, which is much, much larger. So again, you see sort of the breakdown of the small set expansion type behavior. And, if you only looked at like standard expansion before, sure, 1/2 sounds pretty good. But when you're looking at small set expansion and its like relative applications, you really need this type of behavior. This gives you a much, much stronger characterization of expansion throughout your graphs. Okay, so in products, we seem to have sort of a complete breakdown of this theory. We don't have small set expansion. We don't have hypercontractivity. What can we do? Well, again, Noam at the end of his talk suggested a solution to this, which was maybe really these are sort of the only problems that not maybe just the dictators, but sort of local functions, things like juntas, that as long as I avoid this type of behavior, that I could reprove some version of small set expansion or the Bonami lemma. This is typically called global hypercontractivity or hypercontractivity for pseudo-random sets. So what was really the problem with 1i? Why did it fail this type of behavior? Well, 1i is dense in some restriction. This is sort of the key issue. So 1i itself is a sparse function, right? It's a function with density p, but as soon as I restrict, as soon as I fix the ith coordinate to be 1, I fix one value of my product, now the density of the indicator is 1, right? It jumped from being a very sparse function to an incredibly dense function and a single restriction. And the noise operator is sort of a global process. It doesn't see the fact that this it doesn't see this jump in density in one coordinate. And that's sort of what has gone wrong here. So we need to avoid these functions like juntas that upon restricting to a few things become extremely dense. So that motivates this definition of global functions or global sets. So we'll call a function f that maps this product space to the real. You can do it for the reals. I'm just going to do Boolean functions for simplicity. And we'll call this epsilon I global. basically if for all restrictions of I coordinates, my function remains sparse, has density less than or equal to epsilon. So I guess formally I should write for all subsets tau of, or for all tau in A choose I, so for all possible sets of coordinates, and then for all values that I can fix those coordinates, so for all z tau in omega tau or possible tuples to fix these two, that the expectation of f conditioned, let's say x conditioned on the fact that x at coordinates tau is fixed to be values z tau should be less than or equal to epsilon. So, okay, like we said, the dictator clearly fails this definition, right? I can find some one coordinate to restrict to where it's one, where this is one. It's not going to be less than epsilon. And in general, we can hope to prove that these functions will indeed satisfy Bonami and small set expansion. And indeed, this was proved in 2016-ish by Ivosh, Lifshitz, Long, and Minzer. And I think independently by O'Donnell and Zhao, although somebody should correct me if that's wrong. They proved the following theorem. Maybe I'll write it over here. I'm just going to write it in small set expansion form because I haven't defined for you over product spaces what Fi is. There's a decomposition called the Efron-Stein decomposition that I don't know, maybe if later people will talk about this or not, but I'll just do the small set expansion version. But know that there is a version that's the Bonami, like true sort of hypercontractive type behavior. Which basically said that for any product space, again, there's a more general version of this theorem, but let's fix I to be like log 1 over epsilon. This is for the same reason that we saw when Noam did the proof of small set expansion, that he sort of broke the sum up into Fourier levels below log 1 over epsilon and above log 1 over epsilon. So I'm going to sort of do the same thing here implicitly in my pseudo-randomness global assumption. So sufficiently global functions expand near perfectly. Or I'll just say have small set expansion. That in particular, if we look, so I guess formally we haven't defined the analog of the noise operator over a general product. But you can imagine what it is for every coordinate independently. I resample with respect to the product distribution with probability 1 minus rho. We saw this in the p-bias case. It's a very natural definition to extend. So the probability over x and then y drawn from some noisy version of x, that's y. So I define this for Boolean functions. I'll just write shorthand. Let's say that f is the indicator for the set A, so that we match the notation over here. Is greater than or equal to 1 minus epsilon to the c. So again, you basically recover this theorem, except I replace density with this notion of being pseudo-random or global. So in particular, like not only should my function be sparse on sort of the empty restriction globally, it should remain sparse up to log 1 over epsilon levels, and then I get this theorem. And what I'm going to try to convince you of today is that this theorem should extend, where I cross out product spaces and I write gamma high dimensional expanders. And this is a theorem for certain notions of gamma HDX. And I'll note that this is in sort of the two-sided gamma HDX case. This is due to Bafna, Hopkins, Hoffman, of its. And then for a version of HDX that are called gamma products, which I haven't introduced yet, and in some sets actually capture the two-sided case and an additional case we'll talk about. This was proved by Gert Lifshitz and Liu. Okay. Are there any questions about sort of this theorem statement or the general behavior on product spaces before we move to HDX? So the rest of this talk will be about HDX. But I wanted to give sort of this intro of why the rest of the talk is something we should care about.
This issue you mentioned was for small P or even for P local?
No, so if you have, good question. So if you have P equal to half, it's a simple exercise to show that every function is epsilon log whenever epsilon global. So up to getting the wrong constant, this actually recovers the P equals 1/2 version of the theorem. And indeed, like sort of the original study of hypercontractivity beyond the cube, people first proved these results, I guess, that are called like generalized hypercontractivity or something like this, that are for P bias cube and more generally for products. And they depend on like the smallest atom probability in the product. And so it works as long as P isn't really small. But then it turns out that a lot of problems, like you really care about this case that the products are super unbalanced. And then you have to use this type of global function hypercontractivity. Okay, so let's actually talk about high dimensional expanders. That's what I claimed to be talking about in this talk, and I haven't done it yet. So what does any of this have to do with HDX? Well, okay, I claim.
Is there an analytic formulation of that, by the way? Like I see that this, I mean, epsilon here is really important, I guess. I mean, you have sort of like a fixed epsilon, but is there
like you want to think of it as like a log Sobolev thing or
hypercontractive?
So, I mean, of course you can phrase it as Bonami, but if you want to talk about it as like hypercontractivity, the noise operator or something like this, you can, but sort of the problem is that you need to recover like the standard statements, you would need to be global all the way up to the top of the complex. Whereas typically in like the applications that are interesting, you're looking at functions that are global up to like some constant levels of the complex. So you could do this, but only for like a very strong definition of global. I don't know if somebody in the audience has a better answer, maybe Don?
Yeah, we do have the statement. So
Okay. But it is for some stronger global notion, isn't it? That you have to cut off the
derivative of all orders.
Yeah, okay. So you have to say something for all orders versus just like up to level. Yeah.
It's sort of like a discrete version of Sobolev spaces.
Sorry, one more question. Yeah. Is this like kind of equivalent to this restricted log Sobolev inequalities that came on?
You mean that we're in these like recent mixing papers?
Just like this global hypercontractivity here is like for a specific class of functions. Is it like equivalent to some kind of restricted log Sobolev?
You mean like the modified of Sobolev?
I don't. Yeah, I don't know. But it's definitely not equal to modified log Sobolev. I mean, it could be equivalent to some sort of restricted version of log Sobolev where I only maximize over global functions, but I don't know. It's certainly not in the literature. Okay, so why have I been talking about product spaces? Well, here's a claim. Products are high dimensional expanders. In particular, they're like perfect examples of high dimensional expanders. They're what are called zero local spectral expanders. So remembering back from last lecture, this was the definition that said every link of the object should be a zero spectral expander. And I should be a little bit careful here. Again, thank you. Thanks, James. I should be a little bit careful because as I think I erased it, but as I wrote products, it's not a simplicial complex. So let me first show that we can always think of a product space as a simplicial complex. In fact, we basically did this last lecture, right? We wrote out the hypercube as a simplicial complex. The correspondence here is exactly the same. In the product, we had this domain omega n and then some distribution pi n. Now I can always move this over to a weighted simplicial complex. where the vertices x0, again, sorry, x1, not topology notation, are again the sum where we append sort of the coordinate for each of these, or the part for each of these, cross omega, and then I think again x, sorry, I should use k. Xk will just be all possible subsets. It's the complete multipartite complex. It's all possible subsets of x1 that has one of each coordinate. So xk, all strings with one of each part or coordinate. And then in this case, I'm cheating because if your distribution is p-biased or something like this, then as James said, we shouldn't just be working over the uniform distribution. We should actually have some family of weights on the complex that corresponds to distribution. So let me just say that in sort of this general weighted case, I look at a simplicial complex x pi, where pi is a family of distributions over each level of the complex. So pi k is a distribution over k sets, and in particular, this is the distribution that's inherited from the product space. So this is just pi to the k. And then these distributions pi I at lower levels of the complex, we won't worry about them too much, but this is generated just by drawing t from pi k and then choosing s of size I uniformly at random from t. So this induces distributions down the entire complex, and everything that we talked about in the last lecture, all these operators, everything transfers to this. All the calculations, et cetera, we did will work if you weight things with the appropriate distribution here. Okay, so in this view, now I want to actually prove that these complexes are zero local spectral expanders. And we basically saw a version of this, right? Arit gave an example. So there was a specific example that Arit gave, which was basically the unweighted case, right? Arit talked about this complex that was n to the k. And this is just the product of the uniform distribution on 1 through n, k times, and this, and she showed that this was a local spectral expander because she looked at the links. If we have this product, say this is the first copy of omega, this is the second copy of omega, etc. In a product space, when we look at a link, what is a link? A link is like I fix some value in some set of the coordinates, and I look at the induced distribution for the rest of the coordinates. If I fix everything but these two spaces in a product, there's no effect on the distributions here, right? The whole point in a product is that I can fix whatever I want, and the rest of the distributions remain independent. So in this case, what I got when Arit explained it was a complete bipartite graph, and this was a zero spectral expander. In our case, it's slightly more complicated because we'll have distributions that get induced on this graph. But again, because we're in a product, the distribution is just going to be, it's still going to be complete. And the only difference is now these edges are weighted, where this is like pi of element 1, pi of element 2, pi of element 3. So I just get edges that are weighted by whatever the distribution pi is on the space. And so what does this look like in matrix form? If I look at the bipartite, like the full adjacency matrix of this graph, and I have whatever, like the left side, what I get is, every row of this, which corresponds to the weights of a given edge, is just a copy of pi. So I just have a bunch of copies of pi here. I have a bunch of copies of pi here. And this is very easy to analyze the spectrum of, right? It has trivial eigenvalues 1 and -1 from being bipartite and stochastic. And then it's rank 2. So all the other eigenvalues have to be 0. So this is clearly a zero spectral expander. Now, you could repeat this analysis so this is like codimension 2, right? I've fixed everything but 2 things, and I've looked at this very simple bipartite graph. Can anyone tell me how to do this further? How did that now induce the fact that I have a zero local spectral expander without going through the analysis for the rest of the links from Arit's talk that isn't somebody who works on HDX? So we saw something called Oppenheim's trickling-down theorem, right? That said, as long as I have expansion in codimension 2 at the top level of the complex, and everything in the remainder of the complex, all the lower levels are connected. And clearly, if I look at a lower level restriction of this, and I look at the base graph underlying the complex, it's going to be some connected object. It's going to be complete T-partite. It just has some weird weightings. But the trickling down theorem immediately says that because it's connected, if I'm a zero local spectral expander at the top, I'm a zero local spectral expander all the way through the complex. And I think it mentioned something like this with matroids, because these are also zero local spectral expanders. But this is enough to immediately get you this result that products are sort of perfect partite high dimensional expanders. I guess to be explicit, I probably should have mentioned, I think I redefined these, but just in case, we call a complex partite if the top level, if it's k-dimensional and the vertices can be divided into k parts, like omega 1 through omega k, such that every top level face has one from each part, right? Just looking at this as a sort of graph object. My partite complex would just be I'm taking three sets or triangles where I make sure to take one thing from every part. So in a sense, high dimensional expanders are, products are perfect partite high dimensional expanders. Notice that really I should say one-sided here, so, right? Because this has an eigenvalue of -1. And in general, when you look at partite high dimensional expanders, the two-sided definition doesn't make sense, right? The top level always has eigenvalues of -1 from partiteness. So the natural definition on partite HDX is this sort of one-sided notion. And for the rest of the talk, we're basically only going to be talking about partite complexes, which have very nice structure that, they have some notion of coordinates that will be very useful and are more related to products. Okay. So we have the products are high dimensional expanders. The interesting thing, of course, is the reverse question, which is, do gamma high dimensional expanders act like products in some sense? So maybe I'll write partite HDX product like. Okay, so this will sort of be our main question. And the hope is going to be that we'll find some notion where HDX are product like, in a sense where you can look through sort of these proofs of hypercontractivity that use types of induction on dimension or degree. And you can sort of hope that I can use the product like behavior of HDX to mimic the proof. And indeed, this does work. And we're going to see sort of exactly the type of notion that allows us to do this. So the first thing that I actually want to talk about is sort of the opposite of what we did before. So before we looked at a product space and we said we can move the product space to a simplicial complex. Now I want to sort of look at the opposite direction. I want to say that I have a partite simplicial complex and that really I can think about it just as a joint random variable, right? If I have a k-dimensional partite complex, I can always think of this as a joint random variable x1x through xk, where I'm drawing a random k set in my object. And then this is the value on the first part and the value on the second part, et cetera, up to the value on the kth part, right? So maybe let me draw an image. So I have my partite complex. When I draw a random k set from this, it's like drawing one element from each component. And I can think about this as generating this joint random variable x1 through xk. Does that make sense as the connection between these? All I'm doing is drawing a random k set and calling this a random variable. It's exactly the same, but it's going to allow us to talk about things in terms of marginal distributions instead of having to worry about links and restrictions and things like this. So now I want to define a notion due to Gerlach, Schitz, and Liu called a gamma product, which is something that I mentioned over here. which is some sort of approximate notion of this type of joint random variable, or equivalently a partite complex, acting like a product in expectation. We'll call this sort of joint random variable, equivalently partite complex, a gamma product if for all marginal distributions, for all marginal pairs. So this is like looking at a marginal graph, right? I get two random variables. This would be like pulling the marginal over omega-1, omega-2, and this corresponds to some bipartite graph, and I'm looking at the corresponding bipartite graph. If two things hold, one, in this sense, xi xj is a gamma spectral expander, one-sided since it's bipartite. And maybe let me be a bit more explicit on why this is sort of a way that your object acts like a product. What does it mean to be a gamma spectral expander? Well, okay, one way to talk about it is a bound on the second largest eigenvalue, but we can also talk about it in terms of how this allows you to decorrelate functions over x1 and xj. Right? So an equivalent way to characterize this that Arit mentioned is that this is true basically exactly when, if I draw, let's say I have a function f that's on the domain of xi, and I have a function g that's on the domain of xj. I want to say that if I draw like a joint pair from this, and I look at sort of the joint expectation of xi and xj over f times g, I want to be able to decorrelate these, right? If this were a product, drawing from xi and xj would be completely independent, and this would be exactly equal to the expectation of f over xi and the expectation of g over xj. So we get this very nice type of decorrelation property. Spectral expansion says that this happens approximately. Right? There's going to be some error term here that scales with gamma and like the, I don't know, something like the square root of the variance of f and g. I don't care too much about what this error term is. The point is that this is approximately true. That on the complex, we can look at sort of this marginal over two variables, and if we have a function on the parts, this is going to let us decorrelate the function into individual coordinates. And while this isn't like pure independence, this is sort of like a notion of approximate pairwise independence. You can think about it like this. But this isn't quite strong enough for us, right? This is saying that each of the individual marginals has this. In a product space, I additionally have the property that if I like condition on, xk being some value 1, then the remaining product is still completely independent, right? Now if I look at the marginal x1, x2, sort of conditioned on xk equals to 1, it doesn't change. It's the same thing. It's still a product. I want this type of behavior to hold as well. And this is basically corresponding to, this would be sort of like having spectral expansion in the base graph of your complex. And the second notion will be corresponding to having spectral expansion in the links of your complex. This says that I want this to hold even under restrictions or conditionings. So in particular, even if I look at any subset of variables S in K without ij, so if I look at any subset of variables outside of I and j, and I condition on them being some value. So just think about it as I'm like, if I were looking at x1 and x2, I fix the values of omega-3, omega-4, and omega-5, and now I look at the conditional distribution on x1 and x2. I want this conditioned distribution to still be a spectral expander. So xi, xj, conditioned on xs equals cs should still be a gamma spectral expander. Okay, does the definition make sense? I should write, sorry, here. So is there a bipartite?
Property one.
So this is also, I mean, these are all one side. These should all be one side. So these are all bipartite. These are all bipartite operators. So I can talk about in the bipartite graph, right? I have like the sort of I to J direction in the graph, and then I have the J to I direction of the graph. So in some sense, I can talk about like two-sided expansion of this individual operator, which would be like the operator norm of this, or I can equivalently talk about the spectral expansion of the entire adjacency matrix. They're all equivalent. Like sort of the only bad case is coming from the partiteness. So usually you can think about these as sort of acting like two-sided expanders would, except you always have this separate like partite part that you have to deal with.
And this is not equivalent to one-sided expansion like HDX expansion, spectral HDX expansion when it's a partite complex?
Yeah, it's a good question. It's the main theory. These are equivalent. So maybe I'll write this. Yeah, great. So James has done my work for me. It's not immediately obvious that these things are the same because in the local spectral expansion, I'm looking at the base graph across many of these variables. And in this case, I'm looking at the bipartite operators between all the variables. But it's not hard to imagine that these are indeed equivalent. So let's write this up. Partite HDX are roughly equivalent to yeah. Okay, so what are the two directions for this? So one is that, let me make sure I don't get the coordinates wrong. Any apartite gamma HDX is a gamma over 1 minus k minus 2 gamma product. And similarly, any gamma product is a gamma over 1 minus k minus 2 gamma partite HDX. So given the form of these, can anybody guess the proof? Let's look just at this case to start. So I claim that we should already know the proof of this. And the reason is that if I look at the definition of a gamma product, if I look at restricting to all of the variables except xi and xj, the bipartite operator here just is the adjacency matrix of the link, right? So at codimension 2, when I restrict to everything except 2 options, this actually coincides with local spectral expansion. So what are we promised in a gamma product? Well, we're at least promised that everything is, we're at least promised at the top level have gamma local spectral expansion. So all you really have to observe for 2 is to observe that the links of codimension greater than 2. So if I restrict to say all but 3 things, now in local spectral expansion, I'm looking at like the base graph on this tripartite thing. Trickling down theorem says that if my codimension 2 links are expanding and every codimension below is connected, then I infer local spectral expansion for the entire object. This is the proof that Arit went through just the case for dimension equals 3, but this is the general case of the trickling down theorem. So it's not that hard to imagine that this is connected, right? All of the subcomponents are expanders. In fact, if I look at any pair of them, they're connected. So the whole thing is clearly connected. So this means that this version is basically immediate from Oppenheim's trickling down theorem.
If you have like measures, so
No, I mean, Oppenheim trickling down theorem captures measures correctly.
if this current one is like, I don't know, as one edge with a tiny mobility of
It doesn't matter. I mean, the distributions are induced appropriately.
Well, and I think it probably is more clear if you just say like, well, in this definition of gamma product here, right? Covariance is really just saying this is a condition on the covariance matrix of the distribution. Right, and then this theorem really just boils down to saying that the max eigenvalue of the covariance suitably normalized is exactly equal to the second eigenvalue of the below covariant. There's no need to go through triple depth.
Okay, wait, say it again.
So what I'm saying here is that, okay, for each of these conditional measures, you can, this thing, write down as a matrix, right? Like the F and G here are just vectors.
Yeah.
And taking the quadratic form.
Yeah, sure.
Matrix. And the variance F, variance G, that's just some extra normalization that you need. So if I normalize the covariance matrix correctly, then the max eigenvalue of that normalized covariance matrix is exactly the second eigenvalue of the slope random walk in your definition of, in the usual definition of HDX.
But in this case, we're only on two components, and typically when you look at the link, you're on many of the components. There's some difference between looking at only the operator between part 1 and part 2, and looking at the operator on the global object. Right, so it's like having local covariance matrices for every bipartite part.
Oh, okay.
But I think it's a very similar view to like the spectral independence view, which quickly we'll talk about. But I think the only difference is largely that in spectral independence, you look at this covariance matrix across the entire base graph. But here I'm only looking at I'm looking at all of these like individual covariance matrices across the parts.
Oh, I see. Okay. All right. Sorry. Okay. That confused. Yeah, my bad.
Okay, now I'm worried I've done something wrong. So no, I think it should be fine, no?
No, I think what Quigley said is correct at the top level. But-
Yeah, at the top level, yeah. What were you saying?
But then you need trickle down.
Then you use triple down.
Yeah.
Yeah.
I got confused.
Okay, sorry.
Only
Sorry.
support.
Yeah, so these are the only, really the only difference. That's really the only difference though. It's like you look at these bipartite graphs between the two coordinates versus looking at the entire base graph. That's the only difference between these definitions. And you just have to show that there isn't really a difference.
What I'm confused about is like if you take the union of two disjunct union of two high-dimensional standards, then you connect them by tiny measure between them. Then it doesn't. You can change about
The local special expansion of the base graph shouldn't be good if you do that. I think.
Yeah, but the links, they are all, they don't care about it. The links are all expanders, but then I was saying that you win the links when you connect these two. Like,
This already arises just if you look at trickle down,
Yeah.
because and just you look at connectivity, it seems like a very weak condition, but it's the usual thing.
I don't think it's I think it's the same, exactly the same that shows up in trickle down. We can discuss in more depth after, and if somehow there's something wrong, we can issue a correction.
Trickle down, I forget, it goes down to dimension 0. Is that?
Yeah, so trickling down implies that if your links of codimension greater than 2 are connected, that's good. We should have a reminder. And the codimension 2 links are gamma spectral expanders. Then all of the links in the complex, all the way down to the base graph, are gamma over. I mean, you can do this a little bit more carefully, but they're all at least gamma over 1 minus whatever I wrote up here, k minus 2 gamma expanders. Okay, so I have 10 minutes. I wanted to sort of sketch the proof of this version. So this actually appeared earlier in the literature. This is a result of Dick Shannon and Denner from 2019. They used it for some agreement testing type things, sort of before it had been introduced in this context. And really, we've already seen the proof. It's just a partite version of the trickling down lemma done again, but we're more careful using these partite operators. So let me at least give you sort of the skeleton of how the proof goes. Where's this? Okay, again, so like Arit said, basically all of the action is at the k equals 3 case, right? This is where we just have a 3-dimensional complex. And the general case basically follows by an induction once you have the 3-dimensional case. So our goal is to bound lambda. So let's call this bipartite operator between xi and xj. The matrix is mij. We're going to show that this is less than gamma over 1 minus gamma. And what do we get to assume? We get to assume that whenever I fix a value in one of these parts and I look at the induced distribution over the remaining parts, that it's a spectral expander. So I sort of get to assume this is going to look a lot like what Arit wrote, that if we look at sort of these conditional version of the operators, if I look at any v in one of these subsets, and I guess v should be in, if we let's for simplicity, let's just focus on I equals 1 and j equals 2. It doesn't matter without loss of generality. So basically for all v in the third part, we get to assume that mv of 1, 2 is a spectral expander, and we want to induce, just like in the trickling down theorem, we want to use this local expansion to induce global expansion. And we'll do this through the following. So we'll use the 2-function characterization of bipartite expansion. We'll say that lambda m12 is equal to the maximum over, I guess f is a function over omega 1, g is a function over omega 2, orthogonal to 1, such that both of them have norm 1. This is just like variational characterization of m12f g. So this is what we want to bound. So again, the high level idea of the proof is we're starting with this global operator. We want to localize, right? Just like we did in the trickling down theorem. We want to somehow first draw something in omega 3 and then look at the conditional distribution here over which we know it's an expander, and then unroll this back to the global expansion of m12. So let's start with functions f and g that sort of realize this maximum. So we want to upper bound m12 f g. And the first step is just a partite version of the first step that was done in trickling down. What we want to say is that this is equivalent. So here we can view this. This is just an expectation over the variable x1, x2 of f of x1, g of x2, right? This is what this bipartite operator does. This is an equivalent way to write it, similar to what we saw with the adjacency matrix in the trickling down theorem. And again, we're going to say exactly the same thing, which is I can either draw from the marginal x1, x2 to generate this sum, or I can draw from x3, and then conditionally I can draw x1 and x2 conditioned on the value of x3. And this will generate x1, x2 with exactly the same distribution. So first drawing on x3 and then conditioning on x1 and x2 is the same as just drawing x1 and x2 from the marginal distribution, right? It's like law of total probability or something like this. So we can say that this is equal to the expectation over, say, z drawn from this third variable over here of the local inner product, right, of m 2 on this. So we fix z here, and we look at sort of the induced distribution on omega 1 and omega 2. And this is equal to these sort of localizations, just like in the standard trickling down theorem. How much time do I have? Five minutes? 6 minutes. Okay, so the proof is really largely the same as trickling down, which we saw in Arit's lectures. So maybe I'll try to just hit the salient components of this. So the idea, just like it was in the trickling down theorem, is now that we've localized, we want to take advantage of the expansion of this operator. We can't do this naively because even though f and g were globally orthogonal to 1, these local parts that are over this restriction might not be, right? So we need to divide f and z into the parallel and perpendicular components, like a standard trick in expansion. So we'll define fz parallel. we'll write this as the inner product of FC and 1 times 1, and then F perp Z will just be F minus F parallel Z. We do the same thing to G, and then we expand out, let's just look at this component. We expand out this inner product, and we get sort of 4 terms. I'm just going to write M12Z as M for simplicity. So we get MFZ parallel, GZ parallel, plus MF perp Z, F perp Z, plus MF parallel Z, G perp Z, plus MF perp Z, G parallel Z. Okay, the point is that these 2 terms die, right? Because this is something that's orthogonal to 1, and this is parallel to 1. This is parallel to 1, and this is orthogonal to 1. So these terms become 0. We only have to work on these terms. And maybe here I'll sort of skip, because this is exactly what we saw. Sorry, I should have written GZ here. But this is exactly what we saw in the trickling down theorem, right? We now applied the spectral expansion here, right? And we moved to gamma norm of FZ perp times norm of GZ perp. And okay, you have to do some calculations here to rearrange things. But I claim that if you use like AMGM and Cauchy-Schwarz a bit, you'll eventually get to the following characterization, sort of rolling things out in the same way that trickling down does, where you'll end up with 1 minus, basically we'll unroll these to F parallel minus F, and that will have some component here and some component F parallel. So you'll end up with 1 minus gamma times MFZ parallel, G parallel Z, plus gamma times FZ, I think just FZ squared plus GZ squared over 2. And recall that this was actually inside an expectation on Z. So when I look at this term in expectation, the expectation over Z of F of Z squared is just the expectation of F, which is 1, right? So this ends up being 1 plus 1 over 2 is 1, and we just get this additional term of gamma. Here we again use this trick that Arit used, where we notice that the parallel parts are really just the adjacency matrices applied to F and G, right? This sort of expectation, this can really be written as like the bipartite operator M13 of F at Z. It's maybe good to formally confirm this if you haven't seen this sort of thing before, but this implies that we can bound this. This is like looking again at the expectation of Z. This is like 1 minus gamma expectation of Z of M13F Z, and similarly M23F Z, which is just the inner product. So moving over here, sorry for the board space. This is just the inner product of M13F and N23G, which we I guess we should have made the assumption at the beginning that this is the worst possible. All we need to do is to bound the worst one of these. So the spectral norms of M13 and M23 are at least as good as M12. So we eventually get to bound this as gamma squared, lambda M12 squared, norm of F, norm of G, but these are both 1. So we end up back at exactly the same equation that we saw when Arit did the proof, which was 1 minus gamma times lambda. So we started with bounding, we started at this guy, which was equal, we chose F and G since this was equal to lambda M12. So this says that lambda is less than or equal to 1 minus gamma lambda squared plus gamma. And you can check that there are only 2 possible ranges of solutions to this. We have the possibility that lambda is greater than or equal to 1. And we have the possibility that lambda is less than or equal to gamma over 1 minus gamma. This is the case that we wanted. In trickling down, we assumed that the underlying graph was connected. So we got this for free. Here, this is not for free, right? You have to actually prove that these bipartite operators are connected. What we know is that the base graph, like we know that we're a high-dimensional expander. And so we know the base graph is connected. In fact, it's an expander. And this means that if I pick any 2 points in omega-1 and omega-2, I can certainly find a path between them, but it might go through omega-3, right? The path might go through the third part. And the key observation, which I don't have time to write out in detail, is that if I sort of write out this path between U and V, I start at U and I go to W1 through WQ V. If I fix some WI that's in part, so say that this goes through the third variable, well, this is partite, so both of the edges have to go out, both the WI minus 1 before it and the WI minus 1 after it have to be in this part. And moreover, they have to be within the link, they have to be within the restriction of WI by definition, which means that these two paths exist in the link of W1, which we also know is connected and is an expander. So I can replace this path from W minus 1 to WI plus 1 in here. I can replace this with a path inside the link. I should do this here. So I can replace with path in the link of X WI, which entirely runs between omega-1 and omega-2. So if I repeat this process, anytime I hit omega-3, spectral expansion, or really just connectivity of the complex, promises me I can always replace it with the path in here, which gives me connectivity of this operators, rules out this option, and gives us the theorem. Okay, I think I'm out of time. Sorry for going a minute or so over.
Questions?
Yeah, you were gonna say something about maybe hypercontractivity, and so presumably this was
Yeah,
a
sure.
step on the path.
So if you look at the proofs of hypercontractivity, so the proof using gamma products is due to Noam, to Lifshitz-Liu. I mean, they do this induction on degree, which I guess is a little different, but so you can look, for instance, basically at the Efron-Stein decomposition. You can look at some proof of the Bonomi lemma based on Efron-Stein, either by doing some sort of induction on N, or you can do an induction on like the degree of the components. And I guess the key observation is that typically when you're dealing with these Efron-Stein components, these are based on averaging operators where I like re-randomize some coordinate set S in the complex. And you can basically do the entire proof just by using the following assumption that if I re-randomize, outside of S, and I re-randomize outside of T, that this is equivalent to re-randomizing over the intersection of S and T. And you can use this gamma product structure to very easily show that on a gamma product that this has spectral norm O of gamma. And you can basically go through these either inductive type degree or dimension type proofs, just repeating this fact over and over, replacing where this is typically where independence is used in these proofs. So if I replace it everywhere with this O of gamma, what I get is a version of the Bonomi lemma, or then as a corollary small set expansion, where everything scales with this O of gamma spectral error.
Where is the global part of it? The global function?
Oh, I mean, this you would see in the proof of like hypercontractivity on products itself. I mean, we showed as an example that like dictators won't work. The proof that I like that shows this is at some point you end up with like some expectation over the sum of the Efron-Stein components squared. Maybe like this. And if you could somehow push the expectations inside, you would get like a 4 norm. But because these are correlated, you can't. And so you look at intersections of S and T, but basically you pull out the maximum of one of these. This is after looking at the 4 norm and doing some calculations. I pull out one of these terms as the maximum, and then you show that sort of the maximum over these Efron-Stein things are exactly like the averages over low restrictions in your complex. And you get some term here that's like pseudo-randomness or globalness times the 2 norm. And this is why you get like a pseudo-random version and the global version of Bonomi.
But you don't lose a dimension factor, I'm guessing.
No, you don't lose it. Yeah, you don't lose anything in dimension.
And the thing you were describing to me when you just use like approximate.
So, sorry. You're asking like.
I'm asking like, so when you go from gamma product to when you want to prove the global hypercontractivity for products.
Yeah.
You don't do like you said there's an induction and you're losing gamma at every step. So the question is, do you lose it?
Yes, the dependence on gamma will depend on the dimension. So you'll, I think current proofs actually, they're really bad. It's probably like 2 to the K squared gamma after you collect, because you're collecting error terms like everywhere through the proof. And currently you collect a huge amount of error terms. So, you know, if you take like a very strong local spectral expander, like the Ramanujan complex or Hoffman and Oppenheim constructions, this is fine. I can set gamma to be as small as I want in terms of dimension. If I have like a real object in nature, like a symmetric group or something, that's not going to fly, right? This error term will be way too large. So this really only works for these like very algebraic constructions of very strong high dimensional expanders. I think it's a very interesting question to get it to work for where you don't pick up these crazy error terms in gamma.
Is there a version of this theory for a non-Partite?
Yeah, so there are 2 answers to this. One is that what I wrote here, this work actually just does the general 2-sided non-Partite case, but it's observed in Noam's work that you can always take a general 2-sided high dimensional expander, and I can embed it into a Partite complex by including every possible ordering of the top level faces. And you can show that if you start with a 2-sided HDX in the first place, you'll end up with a gamma product or a 1-sided HDX in the second case. And so you can always sort of just embed and then do things in the Partite case and pass back. In fact, it's even true that if you look at, we define some Fourier decomposition on general complexes using something related to Efron-Stein here. They actually look at Efron-Stein on Partites. Even if you look at this embedding, like if you embed a 2-sided complex and you look at the Fourier decomposition, it's exactly the decomposition you would get on the Partite complex. So even like the function decompositions match up, and you can sort of always just talk about Partite complexes in this 2-sided case. If you have an unordered 1-sided HDX, essentially nothing is known. This entire theory that I have said, I mean, you can bound the second eigenvalue, which is used for mixing and stuff, but beyond this, we know absolutely nothing. So the 2-sided case sort of reduces the Partite, the 1-sided case is open.
Any more questions?
Okay, so let's thank Max again.